calling for Dr. Payne.
Yes, you must be Sunny?
Yes, I received your email.
Yeah,
okay.
I received yours. Thank you very much for taking the initiative to find out what we're doing here.
Yeah, I would like to know about your research project with biofuels and how you guys are doing.
Yeah, I'm happy to explain it to you. These are our babies.
Okay.
That is digester 1. This is digester 2. They're made of IBC tanks, which are international bulk container tanks. They're the ones you see on pallets, these white polypropylene tanks in the cages.
Right.
And they ship everything in them. They ship everything from salmon roe for caviar. I mean, not caviar, that would be caviar. It's a different fish.
Right.
Salmon roe for sushi. They would ship in them chemicals. They'd ship vegetable oil. You name it. This is the international container for that kind of worldwide commerce. And so they're pretty easy to find in every country in the world, which is why I decided after building biodigesters out of various local materials that I would concentrate my efforts on something I knew everybody could get.
Right.
We were building in Alaska and we couldn't find the usual tanks we were using in Cairo or in Kenya or Tanzania. So we asked what they did have, and there was a fish processing factory.
Okay.
And they had a bunch of these used.
Okay.
So we decided to modify to those. They're a uniform size. They're each 1 cubic meter, which is 1,000 liters.
Okay.
In gallons, that's about 275 gallons.
Do you fill it all the way to the top when you
Okay. We do. So what we do is we take the empty container, which is light enough that 2 people can carry it upstairs.
Right.
And you can roll them down the street if you have to when they're empty. So you can get them places. They're not extremely heavy. I mean, the cage is about the heaviest part with the pallet. They're very robust. Then to get them into a room like this, they're too big to fit through the door, so we removed the plastic tank from the cage and we jumped on it until we collapsed it and put it through the door, and then it pops back out. A really strong plastic. And then we cut the cages in half, and that enabled us to then get the cages in the door, and then we reassembled it and used zip ties. You can see that yellow zip tie. We zip tied it and screwed it back together so that the cage is holding. And then we insulate them with styrofoam so that they can maintain their temperature. What we're trying to do is we're trying to simulate the stomach of a cow. Or stomach of a horse. These animals have fairly large stomachs, and in their stomachs are water and food and bacteria. So by simulating the stomach, then we feed it, and the idea is if you start out by taking horse manure, so this is a bunch of horse manure. The horse manure has in it the bacteria that were found in the horse's stomach. Cow manure would have the bacteria that are found in the cow's stomach. And that bacteria is a consortia of various microbes, some of which are methanogenic, meaning they produce methane. They're anaerobic. They're dying right now because they're exposed to the air, but I'm hoping enough are kept alive in the center of any particular fecal pellet that we can reconstitute them once they're underwater where there's no air. And this is going to Manhattan for a mini digester that we're making. So we use horse manure. I used about 9 bags of horse manure in there.
So you add the horse manure, then you add water.
Warm water at body temperature.
Body temperature,
So it simulates the inside of the horse.
So would it be different if you had the same setup outside?
You'd always want it to be, you want it to be at body temperature, but they can survive and produce gas between about 13 degrees Celsius, which is something like 50, 55 degrees Fahrenheit, all the way up to 45, on the outside 50 degrees Celsius, which is getting up toward, 140, I don't do Fahrenheit.
Yeah, like 140.
Something like that. So they have a range. Their optimal temperature is 37 degrees Celsius, which is 98.6, body temperature.
Body temperature, 98.67.
Yeah, what that is. So you have the 37 degrees is what you want them at, but that's hard to maintain, and we don't worry too much about that. We fill them with warm water, we insulate it, and when we feed, we're going to feed with warm water. And try to keep the temperature up, and we'll be monitoring it. But if it stays, probably in this room, because it's a warm room, it'll stay above 25 degrees Celsius. We should get some good gas.
Which is good.
Output. This is the cow's mouth. There. This is the cow's mouth. This is his throat, or her throat. Cow's a she. This is the esophagus, and it goes to about almost to the bottom, but it leaves enough space for the food to flow out.
To flow out with the water that you're
right.
ready for. Okay.
So imagine at the bottom of the tank is where the floor is. We're leaving a space and letting the food flush out whenever we feed it.
How much water are you adding as well?
Generally,
you're adding this and the water.
Well, this and the water first.
You have
so
to be balanced. The water is in there already.
Right. We filled this with water. We pour the manure in, and then we seal it and we let it sit for 3 weeks.
Okay.
And that's how long about it takes for the fermentation to occur, for the bacteria that are anaerobic to bounce back from the injury they received when they left the horse or the cow.
Okay.
So that takes about 3 weeks to build up the population. That's what's going on in this tank right here.
How long has that one been?
That's been there for about a week.
Okay.
So it hasn't made any methane yet. It's making gas, but it's making carbon dioxide.
Okay.
That's what happens for the first couple of weeks. Then eventually the CO2 content drops and the methane level goes up, and eventually you get a mix of 70% methane, 30% CO2.
Which is what you want? Or?
You'd love to have 100% methane, but you're not going to get it.
Okay.
And you don't need it. It burns fine at 55% methane, 50% CO2. It burns.
Okay.
At 60-40, you've got really good burning. You can cook on it. You can run electric generators. You can do everything you can do with natural gas.
Awesome.
At 70-30, you've got a higher energy content per unit volume. And so if you could get it higher, you'd want to, but we don't worry about it. If it burns, we're happy.
Okay, good.
It's free fuel.
Got it.
So we wait for 3 weeks for the methane content to get to the point where it's flammable. And once we light it and we know that it's flammable,
right.
That's when we start feeding it. Hold this up for a second. And the way we feed it is we use one of these. Have you ever seen this before?
Nope.
You should have looked underneath your sink.
Oh, really?
Yeah, this is just a standard InSinkErator Evolution compact food grinder.
Oh, okay. So it's like a food grinder.
Yeah, waste disposal. Some people call them garbage disposal.
Okay.
We call it a feedstock preparation device.
All right.
Preparing feedstock for the biogas. And this company has been supporting us, and they donated the InSinkErators for Mercy College that we're using. So they donated 4 of them for us to use. And one will go in Manhattan, and one is here, and then there's going to be another one on a bicycle that's going to be here, not powered by electricity, but powered by human pedal power.
Ah, okay.
For not only for exercise and workouts, so we can get those wonderful sculpted bodies, but also because there's many places in the world that don't have any electricity.
Right.
They can still make biogas. So the InSinkErator food waste grinder is the teeth and jaws of the sacred cow. And then it goes down the throat, and then it goes down the intestines. And so that's the stomach of the cow. And then the cow has got to belch and fart methane. So we have this one here, which is at the top. Gas rises, so when this is in the tank, the gas will be at the highest point, and it will belch and fart out here.
Okay.
These pipes go to the middle of the tank. They'll be underwater, even if there's gas building up. They'll stay underwater, and they're going to take the pee of the cow, which is the fertilizer.
Right. So you take that out.
So that comes out the middle, and the reason it comes out the middle, maybe you can guess why.
It comes out.
Gas
what?
has to come out the top.
Okay. Because the water is all the way up to here.
Yeah, and if the gas is being produced, it could get as low as here, and you don't want the gas to escape.
No.
The gas is from here.
Right.
The other reason, though, is
you want
because
to collect the gas.
if you imagine this being in the tank, as you put the food in and it goes to the bottom, the protein and some of the carbohydrate will be more dense than water and will sink to the bottom, and the bacteria will eat it and make gas, which will bubble up. But the lipids, the fats, float, right?
Yes.
You see fat floats on the top of water. So the fats are going to rise to the top, and the bacteria are going to come and try to eat them and make gas.
Okay.
So you don't want to take your water out of the bottom or out of the top, because then you'd be taking energy-rich food out before the bacteria had a chance. So we put it in the middle under the assumption that after the bacteria have eaten the heavier solids on the bottom and eaten the lighter solids at the top, that the middle will be where the dead material is that's been eaten, and that's where we take our fertilizer out.
So it's like an equilibrium.
Right. And the fertilizer will then contain everything the bacteria haven't eaten and a lot of stuff that the bacteria have added. And it's the richest fertilizer the world has ever known.
Okay.
Better than anything you could buy. Great for hydroponics. It's a liquid fertilizer. It comes out water soluble. Everything is going straight to the roots of any plant you give it to. It doesn't sour the top, doesn't block photosynthesis. It goes right into the soil to the roots. But it's got everything that you threw away. When you threw away your food, you were throwing away banana peels and potato peels and tops of carrots and things with dirt on them that you washed off. All the nutrients, the micronutrients, whether it's zinc or molybdenum or trace amounts of copper or it's calcium, magnesium, everything is in the stuff we're throwing away. It's not in the food because we eat starch, basically.
Right.
And we throw the best part away. And that's the fertilizer that needs to make it back to the plants to keep the cycle of life going.
Right.
But instead, we flush it down the drain and into the river and into the ocean, and it never gets back to the farm. And then farmers have to buy fertilizer and bring it to the farm.
Okay, so you're not only making the gas for energy, you're also making the fertilizer.
The world's best for the most nutritious food. There can be no malnutrition because you're returning back to the soil everything that was taken out.
Great.
So the idea is that we would grow on this rack, which is now just filled with junk, we're going to grow plants for the cafeteria. And we're going to use the cafeteria waste, grind it up in measured quantities, make gas, use the gas to cook, use the fertilizer to grow the plants, which go to the cafeteria, to be cooked on the gas, to be eaten, so that then the waste goes here and goes back in. The only
so they make a cycle.
Right, and there's only one thing missing. What's that? In the cycle, if you grow food, eat it in the cafeteria, grind the food waste, put it in the tank, get the fertilizer, there's still a piece of fertilizer missing.
There's still a piece of fertilizer.
Yeah, so the cycle's not complete. Because imagine this starting at the beginning of the chain. You go to the cafeteria to eat. You eat. You take all the waste that you don't eat, you put it through the grinder into the biogas tank. But what about
person?
Stuff you ate.
Right.
So there's what you crap out.
Right.
That's fertilizer too.
But you're not doing that.
Well, we will. We have to. Okay. We have to investigate that. So we'll do a controlled experiment in this tank, seeing if we take measured amounts of human manure, they call it.
Right.
We're not going to make students do this. We're going to do it in a laboratory
okay.
way. But taking human manure and figuring out how much gas content do you get from that and what kind of fertilizer, which we'll analyze, because we have all the equipment in here to analyze.
Right.
Looking at the bacterial count, looking at the coliform count, looking at the methanogenic. But your gut, just like horse's gut, also has methanogenic bacteria that make biogas.
Right.
So we're going to do an experiment to see, can we even start a reactor on human manure, and how does it perform relative to one that starts on horse manure?
To compare them.
Because in the cities, in the burgeoning slums of the world, there are no horses.
Right.
But there's people.
Right.
And they have a source of bacteria in their own gut that they carry with them that can be used to turn their food waste into methane and into fertilizer. And we're doing a workshop in Chad, in Africa, this summer, and we'll be building much larger than this, big biodigesters in a prison. And all they have are toilet wastes and kitchen wastes. And there's no animals.
Okay.
So we'll go out to Chad, one of the worst prisons in the world.
Wow.
And it's filthy, and we have to clean it up. Similarly, we have colleagues who are building biodigesters in Nepal near Mount Everest Base Camp in a village called Gorak Shep, where we visited. And there's so many trekkers going up to Mount Everest that everybody's crapping all along the trail, and it's causing water contamination for the villagers. All this crap going into the river. So they're building a biodigester to take all of the human feces and ferment it and generate gas to help keep the village warm, because it's up in the frigid Himalayas.
Right, okay.
And we're going to be adding the component of the bicycle-powered incinerator that the engineers there have developed, so that people without electricity can grind up the food waste and add that to enhance it. And that's because food waste has 100 times more energy, roughly, than fecal waste.
Right.
Because when you eat the food, you use up all the energy you go jogging and disco dancing. But when you put it through here from the food waste, you get a lot more energy. So they'll use both the human manure and the food waste and get a lot of energy.
Got it. Okay. Perfect.
It's a total solution. I mean, think of it.
Definitely.
All toilet wastes and all kitchen wastes, all market wastes, all slaughterhouse wastes, all can be biodigested, produce a safe, rich fertilizer, and safe, clean-burning methane, meaning there will never be, if people adopt this, cholera, typhoid, amoebic dysentery, all the waterborne diseases associated with people's crapping in water.
I was going to ask about that.
Finished, eliminated.
When you put it in here, let's say somebody with cholera, you use their fecal waste
that will not affect the whole experiment? That will not contaminate the whole?
No, what would happen is that the Vibrio cholera bacteria would have to compete with a well-established colony of all these different microbes that are making methane.
Mm-hmm.
They go in there and they try to establish themselves, but it's not their environment, and so they would actually end up being killed and eaten, reducing the pathogenicity. Now that doesn't mean that we would take fertilizer from these and directly put it on a garden.
No.
We would never pour it directly into a river.
Okay.
What we would do is then take that fertilizer if we suspected somebody had cholera, or if we're in a village where we don't know if people do or not, and we would then aerobically compost that first and apply it to tree crops where the roots would destroy any other pathogens.
Okay.
But what wouldn't happen is it would never get flushed into the water supply.
Okay.
It would go to plants that could take care of it after it had been aerobically cured, after 99% of it had been cured in the digester. And that's the usual figure, is 98-99% of all pathogens are eliminated inside the tank.
Which would definitely reduce sickness and stuff.
Right. So then you've got waterborne diseases, finished, no problem. You've got fertilizers, so you have very nutritious food being grown. You don't have to worry about water because you're taking dirty water, gray water that has soaps in it and all the stuff that contaminates rivers and streams. You're putting the soapy water in there and the bacteria are eating the soaps.
Right.
Because they're, glycerol and fatty acids, that's what makes up soap.
Mm-hmm.
So soaps, yes, can kill bacteria when they're new, but after the soap has been used, it doesn't kill bacteria, bacteria eat it. And that's why gray water stinks, because the bacteria are eating the soaps.
And even if diluted as well.
Yeah. So we'll put the soaps in there, and the bacteria will eat it and turn that into fertilizer. So no more eutrophication problems because of soap, phosphates, all the things that are bad for bodies of water are now safe because we're eating them.
Okay.
Getting more gas from that. So that takes care of that problem. And then you have air pollution. Methane is completely clean burning, no carbon monoxide, just carbon dioxide and water when it burns.
Okay.
A little bit of hydrogen sulfide, which smells only when the gas is not burned, which is good, because then you know if the gas has been left on, just like your gas bottle. But when you do burn it, no smell. You cook on it in the house, no smoke, and that means thousands and thousands of women and children who are dying every year from respiratory illness burning charcoal or firewood never die again. We were doing this in Tanzania near the Gombe Stream Chimpanzee Reserve.
I'm thinking about the atmosphere as well.
And they don't have to deforest because there's no need for the women to go out there with their machetes and chop down firewood to bring it, haul it home. They travel 2-3 hours to get their firewood. They burn it in the hut. They're dying. Their eyes are tearing. No, they just turn a tap. This is outside the kitchen. Clean burning methane inside. No more respiratory illness. So we simultaneously solve waterborne disease, deforestation, indoor air pollution, sickness, and energy problems, and agricultural. And that's why we're considering this the simplest of all development technologies that everybody needs to have as a baseline.
Got it. So what would be the next step? To make people do this regularly, or make industries do
Industry's
this?
already doing it. Incinerator has a deal going with the city of Philadelphia where they're taking restaurant, cafeteria, and home organic waste. It goes to the waste treatment plant through the water system, through the pipes, and then they capture the methane, generate electricity, and heat with it hot water and sell it back to the city.
Right.
So Philadelphia's doing this, Milwaukee's doing it, Brooklyn started a pilot project. Stockholm, Sweden, they even run buses, trucks, and cars off of it. They compress it and purify it.
Great.
Yeah, it is solar energy that's available all the time because photosynthesis is where the energy is captured in the plant waste. So it's the most obvious solution, and yet it's so unobvious to so many people.
Yeah, because it's not widely used.
Yeah. So we at Mercy will be pioneers, will be leaders.
Great.
Welcome aboard.
Thanks.